Good afternoon. I'm really happy to be here to present our paper. And our paper is about using data mining techniques to solve a computational problem from the insurance industry. It is a joint work with Professor Jimmy Huang from York University. And Jimmy is also here. This is the outline of my talk. So first I will talk about the computational problem from the insurance industry. It is a problem related to variable annuity. Then I will describe the data mining framework used to address this computational problem. Finally, I will show some numerical results. So how many of you have heard of variable annuity? So you can raise your hand. Okay, not many. Actually, variable annuity is a life insurance contract between a person and insurance company. So this graph shows a typical cash flow between the policyholder and the insurance company. So usually you pay money in form of premium to the insurance company. The insurance company save your money in separate account. So you can invest this money in market, so like equity or bond. So you can. So if the market go up, your money will grow. So if market goes down, insurance company provide some protection. So that's why you can take a withdrawal from the account. But if your account value is depleted, insurance company sometimes has to use its own money to cover the shortfall. So if your guaranteed amount is higher than the account value, the insurance company has to cover the shortfall. And there are different types of guarantees. So this is really special about this product. So all of these guarantees are financial guarantees. So it's called GMXB, so guaranteed minimum sum benefit. So for example, there are two types of guarantees, death benefit and living benefit. So guaranteed minimum death benefit. So if the policyholder dies, the beneficiary of the policyholder gets the death benefit. So living benefit, there are different kind of living benefit. You have the guaranteed minimum income benefit, guaranteed minimum maturity benefit, and guaranteed minimum withdrawal benefit. So different kind of benefit, you can do different things with the policy, and it's very popular in US. Now this is an example, shows how risky this business is. So this is a very simple example. So a variable annuity with a GMW feature. So the policyholder purchase this guarantee. So he can withdraw 80% every year, and he invests 100,000 to this account. So this is a very bad market condition. So after the 7 years, the account value is depleted, right? But because of the guarantee, the policyholder can still withdraw money from the policy because the initial investment is $100,000. So he should be able to recover the initial investment because of the guarantee. So after 7 years, there's no money in the account, but he still takes withdrawal. So insurance company has to use its own money to cover the shortfall. So under this bad market condition, so the insurance company lost money. Right? And in all policies, it's really unlike the traditional policy, like life insurance. If you issue 1,000 policies, life insurance, it's not possible that all 1,000 people die at one time. Right? It's not possible if you underwrite the policy appropriately. But for this kind of guarantee, if the market goes down, insurance company lost money on all policies, not just one policy. So it's very risky. And this graph shows the stock price of the top issues of the variable annuity in the last 10 years. So you can see during the 2008 financial crisis, some company lost 80–90% of the stock, the capital of the stock price. So you can see. And during that time, a lot of companies lose money. They needed to get actual capital from bank to survive. And the chief actually from one company just get fired because of this event. he didn't manage risk appropriately, and we had him in our actual science program. So my colleague says, in bad market condition, we get people from company. In good market conditions, we get money because the insurance company has to make money. So now, insurance companies, they use some kind of hedging technique to reduce the risk, the financial risk, because they still want to keep this guarantee feature in variable annuity because it's a very good marketing feature, so they can sell the product easily. But they also do not want to take the financial risk, so they hedge the risk. So dynamic hedging is usually used to mitigate the risk. To hedge the risk, they first need to quantify the risk, so that they need to calculate some sensitivities of the fair market value of this guarantee to major market indexes. For example, they need to calculate delta, the sensitivity to the market index like S&P 500. Also need to calculate some other sensitivities like interest rate because this is a very long-term contract, so it's very sensitive to interest rate risk. And because the guarantee are very complex, so it's not like the option you see traded in the exchange. It's very complete option. It's kind of like a put option, but it's embedded in this insurance product. So they use Monte Carlo simulation to calculate the fair market value because there's no closed form formula. So one problem with the Monte Carlo simulation is it is very time consuming because you have a large portfolio with 500,000 policies. You need to calculate the fair market value for each policy, then add them up to get the total. So very time consuming. Let's look at an example. Suppose you have a portfolio with 100,000 policies. And the Monte Carlo simulation uses 1,000 scenario. So you can think of scenario is just this status of the world in future. So you can go up, then go down, then go up, just the market, the movement of the market. And use 30 years for projection because long-term contract, the life insurance product is usually long time. So you need to project 30 years at a monthly step. So then you have to do 36 billion cash flow projections. Suppose you have a computer that can process 200,000 projections per second. You take this computer 50 hours to calculate the fair market value, just one market condition. If you want to do some sensitivities, you need to do more calculation. So right now, insurance companies, they solve this problem from the hardware perspective. They just rent a lot of computers, say thousands of CPUs to calculate this every day. Some companies even use GPU to calculate this. So in our work, we try to solve the problem from the software perspective. We build a mathematical model to speed up the calculation. So our idea is this. So first, we use a clustering algorithm to divide the portfolio into clusters. So from each cluster, we select one representative policy. Then we run the Monte Carlo simulation on this representative policy to calculate the fair market value or other items like the Greeks. Then we use the representative policy. Right? This is the independent variable. This becomes the dependent variable. So you can build some regression model. Then we use the regression model to calculate the fair market value of the whole portfolio. Because the Monte Carlo simulation is very time consuming and the regression model is very fast, so you can reduce some runtime significantly because the number of representative policy is usually smaller than the number of policies in the portfolio. But it's not too small. You cannot just choose 2 or 3 representative policies. You cannot get good results. So that's why we need to divide the portfolio into small, but not too small. So you probably need 100 or to 500 representative policies. So there's some requirement on the clustering algorithm. You need a clustering algorithm that can divide a large data set into a large number of clusters efficiently. mostly traditional algorithm, you focus on the small number clusters, so usually less than 10. Right? You look at the less than 10 clusters, but 10 is not enough. We need 100 clusters. So we need to divide the data set into 100 clusters. So we need an efficient algorithm. We try to k-mean. So if you divide 10,000 data points into 100 clusters, and the dimension of the data set is say 20, it will run 1 day, and you cannot get results. So we propose to use a TF7 plus algorithm. It's called truncated fuzzy c-mean. The double plus means how we choose the class CD. It's based on the k-mean plus algorithm, how we choose the initial class center. So this algorithm is very similar to fuzzy c-mean. The only difference is the fuzzy partition matrix. So each law you have at most T non-zero entries. That means one data point can only belong to at most T clusters. So then at each iteration, you only calculate this distance, a small number distance. You don't have to calculate the distance between all clusters because you have a bigger number of clusters. So you cannot calculate all the distance to all clusters to assign the point. Right? You just calculate a few of them because only a few of them have a high degree of membership. So that's the idea. So this is the objective of the function. It's very similar to fuzzy c-mean, but the only difference is we have a constraint on this U, the fuzzy partition matrix. So each law cannot have more than T non-zero. So we build this. We use this algorithm to select representative policies. For regression model, so once you have this representative policies, you run Monte Carlo simulation to calculate fair market value. Then you have the deep independent variable, right? That's the policy features. You also have the dependent variable, that's the fair market value or Greeks like delta or rho. Then you can build a model. So you have X, you also have the Y. Then we propose to use Kriging, because Kriging works well for different distributions, even though it's refers to Gaussian processor regression, but it still works empirically. So it is just a weighted average from the representative policy. So for example, we have K representative policy. We just use a weighted sum of this fair market value of the representative policy to estimate the fair market value of a arbitrary contract X. And this Kriging weight, Wij are the Kriging weights you solve from the linear equation system. So this, you calculate the pairwise distance of all these representative policies. For this study, you calculate distance between a new country policy to all the representative policies. It's like an interpolation. So we don't have to solve this equation for each policy because these are the fixed for all the policies. So if you only want to get the estimate at the portfolio level, there's a very efficient way to do that. You can just solve the equation once. You don't have to solve every equation for each policy. So you can just add all this equation in both sides, then you get an efficient solution. So we have two parameters to simplify the application. So alpha we usually take to 0. That means exactly interpretation. So for example, if X is one of the representative policy, then the output is exactly the fair market value of that policy. So the interpolation passes the point. So if alpha is less than 0, you smooth out. So like a regression, least square, right? You smooth out. So we usually let alpha 0. Beta, you can take to be the 95 percentile of all the distance. So you don't have to fit the model. Just use the rule of thumb, you get a very good approximation. Now, let me show you some numerical results. So we have a portfolio of synthetic variable policy. Then we use a Monte Carlo simulation to calculate the fair market value, delta and rho of each policy. So delta is the sensitivity to the equity, the S&P 500. So rho is the sensitivity to interest rate. So for example, the fair market value here is most are positive. That means it's bad for the company. Because fair market value is the benefit, subtract the fee collected by company. So the distribution is a very fat tail. Now we use two risk measure, validation measure. So firstly is the percent error at the portfolio level. Another one is R square for the individual. So, and the company are interested at the portfolio level because they want to hedge the whole portfolio. They do not want to hedge each contract separately. They are not very interested about the fitting of at the individual level. So this table shows the validation measures for different K. So K is the number of clusters, also the number of representative policies. So when K equals 100, we already get a good results at the portfolio level. At the individual level, the R square is not that high. But if you increase the number of representative policies, you can increase the R square. So if you have more training data, then you get better prediction accuracy. So if you increase further the K to 400, so use 400 representative policies, the R square continually increases. Now let's look at the fitting at the individual level. We have the scatter plot of the fair market value of the Monte Carlo simulation and the fair market value of the Kriging. So it's not a look at that great because Kriging is assume normality. Gaussian process means the data should be normal distributed. So K equal to 200. So it's become better now, right? Become a little bit better at the individual. If you use K equal to 10,000, use all the data, you get an exact straight line because Kriging is exactly interpreted. Now let's look at the runtime. If you use Monte Carlo simulation for the whole portfolio, it will take the computer 72,000 seconds. But if you use our data mining framework, you can even use 400 representative policy. It can be done 3,000 seconds. So you can reduce the runtime significantly. At the same time, you still have accurate approximation. And the company usually 5% error, they don't care, it's not a material. So this has a very promising solution to the problem. To sum up, so in this paper, we propose the data mining framework to address problem. And there's the two major components, a clustering algorithm and a predictive model. And this can reduce the runtime significantly. And this research is supported by some grants. So a grant Center of Actual Science grant from the Social Equity and some grants from the Canadian government. I think I will stop here. So I'm happy to take questions if you have any.
Hey, thank the speaker.